Hi everyone! Today we're going to talk about transaction isolation levels in SQL. This topic often comes up in technical interviews, but it's also one of the most confusing concepts in databases. My goal in this video is to make it simple and clear so that by the end you'll really understand what each isolation level does and when to use it. So let's get started. In a database, tables are constantly queried within transactions. Every transaction starts with a begin statement, followed by one or more queries, and finally a commit, which finalizes the changes. But at what point do these changes become visible to other transactions? Imagine multiple transactions running in parallel. So here we have 5 transactions querying the table. What state of the database does transaction 4 see at a given point of time? By that moment, 2 transactions have already committed their changes, and the third one has executed a query but hasn't committed yet. Should transaction 4 see the results of transaction 2 if those changes were committed after transaction 4 started? In SQL, there is a configuration that controls how transactions interact with each other. This configuration is called the transaction isolation level. By setting the isolation level, you define the rules that determine how the current transaction interacts with other transactions and which results are visible to it. In other words, it provides guarantees that certain unexpected behaviors, known as anomalies, are prevented at each isolation level. Let's take a closer look at the relationship between anomalies and isolation levels. The first anomaly is a dirty read. It is a phenomenon when a transaction reads data written by another uncommitted transaction. Here is an example. One transaction updates a balance and then rolls back the change, while another transaction reads that uncommitted balance. The problem is that the second transaction works with data that is not actually valid. Next is the non-repeatable read anomaly. It occurs when a transaction rereads data it has previously read and discovers that the data was modified by another transaction that has already been committed. Let's go through an example. The first transaction reads some data, the balance in our case, and then makes a decision based on that value. For example, it decides to delete the row if the balance is 0. So the next step is deleting the row. At the same time, another transaction updates the balance in between these two operations. The anomaly is that the data changes after it has been read, but before the transaction acts on that read. As a result, the transaction makes a decision based on a stale data. Another transaction anomaly is called a phantom read. It is quite similar to the previous anomaly. The difference is that the decision is made based on the number of rows, and this number changes due to a concurrent transaction. For instance, suppose we want to limit the number of accounts per user. Before inserting a new row, transaction 1 checks whether any accounts exist for a given user. After getting 0, it decides to insert a new row. However, another transaction commits an insert in parallel. The issue is that a predicate-based decision is made on a set of rows that is no longer stable. And the last anomaly we need to cover is the serialization anomaly. It occurs when concurrent transactions produce a result that cannot be obtained by executing those transactions in any serial order. A classic example is a table with doctors who are on call. So we want to enforce the rule that at least one doctor must always be on call. Initially, both Alice and Bob are on call. In the first transaction, we check the number of on-call doctors, get a count of 2, and decide to mark Alice as not on call. In parallel, another transaction performs the same check and decides to mark Bob as not on call. As a result, no doctors are left on call, exactly the situation we wanted to avoid. So if the transactions were executed sequentially, this would not happen. If Alice were marked as not on call first, the second transaction would not decide to mark Bob as not on call, and vice versa. So therefore, the result of this group of transactions cannot be obtained by executing them in any serial order. This is the meaning of the serialization anomaly. Going back to transaction isolation levels, the SQL standard specifies which anomalies must not occur at each isolation level. There are 4 transaction isolation levels. The least strict one is called read uncommitted, and it allows all anomalies to occur. However, this mode is not supported in PostgreSQL and is always upgraded to the next level called read committed. The next isolation level prevents dirty reads, and this level is called read committed, and it is the default isolation level in PostgreSQL. When a transaction uses this level, each query sees a snapshot of the database that contains only committed data. So let's assume transaction 4 contains 3 queries. The first select will see only the results of transaction 1. The second select will see the results of transactions 1, 2, and 3, as they were committed before that query was executed. In other words, each query sees all transactions that were committed before the query started, as well as the changes made earlier within the same transaction, so they are also visible. An important point is that modifying statements do not conflict with reads from current transactions. So if 2 transactions modify the same row, no error occurs. The updates are just simply executed one after another. Now let's move on to the next isolation level. The next isolation level guarantees that the non-repeatable read anomaly will not occur. And somewhat surprisingly, the level is called repeatable read. At this level, the data snapshot is created only once at the beginning of the transaction. As a result, all queries within the same transaction see exactly the same data. Looking back at our previous example, both selects would see only the results of transaction 1 because it committed before transaction 4 started. Changes made earlier within the same transactions are of course also visible. However, if a concurrent transaction tries to update the same row, an error will be raised and the transaction must be retried. As for phantom reads, in PostgreSQL implementation of repeatable read, they're also not possible. This is because the snapshot is taken at the start of the transaction, so the set of visible rows and therefore the row count remains stable. Repeatable read is the isolation level defined by SQL standard. Internally, PostgreSQL implements it using a technique called snapshot isolation. Some databases distinguish between these two concepts, repeatable read and snapshot isolation, but PostgreSQL exposes only the standard isolation levels. That could be sometimes a bit confusing. At the highest isolation level, none of the anomalies are possible. This level is called serializable, and it provides the strictest level of isolation. Serializable isolation guarantees that the outcome of committed transactions is the same as if they had been executed one after another, like in a serial order rather than concurrently. It is important to note that transactions are still executed concurrently in reality. So database simply performs additional checks to ensure that serialization anomalies do not occur. In PostgreSQL, this level works similarly to repeatable read, but with additional checks for serialization errors. A snapshot is also created at the beginning of each transaction. If concurrent transactions attempt to modify the same rows, a serialization exception may be thrown, and the transaction must be retried. Overall, this level guarantees that a transaction will have the intended effect and that anomalies such as write queue cannot occur. As always, these guarantees come at cost, possible retries, and lower performance compared to weaker isolation levels. That's all for today. I hope you found this video useful and now feel confident choosing the right isolation level. Thanks for watching, and I'll see you in the next video. Bye!